Good morning, students. I am Kavita Chahal, Assistant Professor in Chemistry Department from Government PG College, Sector 14, Panchkula. Today I will discuss about alcohols. Alcohols are hydroxy derivatives of hydrocarbons. They are further classified as monohydric, dihydric, and trihydric alcohols according as the number of hydroxyl groups present in their molecules is 1, 2, or 3 respectively. Alcohols containing 4 or more hydroxyl groups are known as polyhydric alcohols. Example: methyl alcohol is monohydric alcohol, glycol is dihydric, glycerol is trihydric, and sorbitol is an example of polyhydric alcohol which contains 6 OH groups. 2 OH groups linked to same carbon atom is unstable and lose a water molecule to form aldehyde. Next is aromatic hydroxy compounds. Aromatic hydroxy compounds are classified into two categories. First is aromatic alcohols, in which OH group is attached to an aryl substituted alkyl group. Example: benzyl alcohol. Second is phenols, in which OH group is attached directly to an aromatic ring. Classification of monohydric alcohols. Monohydric alcohols are further classified as primary, secondary, and tertiary alcohols. Primary alcohols, in which OH group is attached to primary carbon atom. Example: ethyl alcohol, N-propyl alcohol, benzyl alcohol. Secondary alcohols, OH group is attached to secondary carbon atom. Isopropyl alcohol and secondary butyl alcohol are example of secondary alcohols. Tertiary alcohols, OH group is attached to tertiary carbon atom. एग्जाम्पल है इसका टर्सरी ब्यूटाइल अल्कोहल. नेक्स्ट, methods of formation of alcohol. Alcohol are prepared by reduction of aldehyde, ketones, carboxylic acids and esters by using different reducing agents. First is reduction of carbonyl compounds. Carbonyl compound can be reduced by catalytic hydrogenation or with complex metal hydrides. First is catalytic hydrogenation. This reaction takes place in the presence of catalysts such as nickel, palladium or platinum. Aldehyde give primary alcohol and ketone give secondary alcohol after reduction. Reduction with complex metal hydrides. The reduction is carried out in lab with complex metal hydrides such as lithium aluminum hydride and sodium borohydride. Lithium aluminum hydride is more reactive and less selective as compared to sodium borohydride. In this reaction, these complexes give hydride ion which attack on carbonyl carbon to form an intermediate which further hydrolyze to give alcohol. Next is Meervin-Pondorf-Verley reduction. This reaction is carried out by heating carbonyl compound in isopropyl alcohol in the presence of aluminum isopropoxide. In this isopropyl alcohol give acetone and ketone give secondary alcohol. Reduction of carboxylic acids. Primary alcohol can be obtained by reduction of carboxylic acid by lithium aluminum hydride. Sodium borohydride does not reduce carboxylic acids. Bowe-Alt blank reduction. This reaction is used for reduction of ester to alcohol and give a mixture of two alcohols, one formed from alkoxy group and second from acyl group. In this method, we use sodium metal and ethanol. Sodium metal give electron and ethanol give H positive ion for reduction. Next is physical properties of alcohols. Alcohol contain hydrogen attached to strong electronegative atom oxygen. So oxygen is more electronegative as compared to hydrogen, and it attracts said pair of electron towards itself and has slightly negative charge, and hydrogen has slightly positive charge. So alcohol is highly polar in nature. Alcohol exists in form of associated molecule with intermolecular hydrogen bond and has band structure. Physical state: lower alcohols are colorless liquid having distinct alcoholic smell and burning taste, but higher members are colorless, tasteless waxy solids. Alcohols contain hydrogen attached to strong electronegative oxygen atom, so extensive intermolecular hydrogen bonding exists between alcohol molecules. As a result, alcohol exists in form of associated molecule, not simple monomeric alcohols. Boiling point of alcohol are much higher than that of hydrocarbon or ether. The high boiling point of alcohol can be explained in terms of extensive intermolecular hydrogen bonding. Amongst different isomeric alcohols, order is primary alcohol has highest boiling point, then secondary, then tertiary. This is because out of isomeric alcohols, primary alcohols are most polar and form hydrogen bonds to a maximum extent as compared to secondary and tertiary alcohols. Alcohols are also soluble in water due to hydrogen bonding, and solubility decrease with increase in molecular weights. Next, chemical properties of alcohols. Reaction involving cleavage of OH bond. Order of reactivity of alcohols in this type of reaction is: primary alcohol is more reactive than secondary alcohol, then tertiary alcohol. This order can be explained in terms of electron releasing inductive effect of alkyl group. As we move from primary to secondary to tertiary alcohols, number of alkyl groups attached to carbon carrying OH group increase from 1 to 3. Due to this, electron density around oxygen goes on increasing, moving from primary to secondary to tertiary alcohol. The result is that electrons of OH bond cannot sufficiently drawn towards oxygen, and cleavage of OH bond decrease. Thus, the order of reactivity in these reactions involving cleavage of OH bond is primary, then secondary, then tertiary. Reaction with metals. Alcohol react with active metal like sodium, potassium, magnesium, and aluminium to liberate hydrogen and form metal alkoxides. These reactions show acidic nature of alcohols. But alcohols are very weak acids, even weaker than water. This is because alkyl groups present in alcohols have electron releasing inductive effect. This causes an increased electron density around oxygen. The result is that electrons of OH bond are not sufficiently drawn towards oxygen, and release of proton is difficult. In other words, the plus I effect of alkyl groups make the alcohol weaker acid than water. Reaction with Grignard reagent. Alcohol react with Grignard reagents to form hydrocarbon. Reaction with organic acid. Alcohol react with organic acid in the presence of concentrated sulfuric acid and hydrogen chloride gas to form ester. This reaction is slow and reversible and also called as esterification reaction. Reaction involving cleavage of COH bond. The order of reactivity of alcohol in this reaction is tertiary alcohol is more reactive than secondary alcohol than primary alcohol. This order can be explained on the basis of stability of carbocation. Tertiary carbocation is more stable than secondary than primary. Reaction with hydrogen halide. Alcohol react with hydrogen halide to form alkyl halide. Order of reactivity of hydrogen acids is hydrogen iodide is more acidic. Hydrogen iodide is more reactive than hydrogen bromide than hydrogen chloride. This order is explained on basis of bond length of hydrogen halides. Primary alcohol, secondary alcohol and tertiary alcohols are differentiated on the basis of their reaction with Lucas reagent. Lucas reagent is a mixture of hydrogen halide and anhydrous zinc chloride. Tertiary alcohols react with Lucas reagent immediately to produce cloudiness due to formation of alkyl chloride. Secondary alcohols react with Lucas reagent less readily to produce a cloudiness after 2 or 3 minutes. Primary alcohol react with Lucas reagent only on heating. No cloudiness is produced in cold. Reaction involving both alkyl and hydroxyl groups. Alcohol dehydrated to form alkene. In the presence of dehydrating reagent such as sulfuric acid, phosphoric acid or boric acid. Next reaction is oxidation. Oxidation of alcohol can be carried out acidified or alkaline potassium permanganate, acidified sodium or potassium dichromate, dilute sulfuric acid and chromium trioxide in pyridine. Primary alcohol after oxidation give aldehyde which further oxidized to give acid. Secondary alcohol first oxidized to give ketone, then further give acid having one carbon less than ketone. Tertiary alcohol also give ketone first, then give acid. Next topic is dihydric alcohols. Dihydric alcohols are compounds containing two hydroxyl groups attached to different carbon atoms in their molecules. Example: ethylene glycol, propane 1,2 glycol, and propane 1,3 diol. Methods of formation of dihydric alcohol. First is hydroxylation of alkene. Glycol are prepared by hydroxylation of alkene by treatment with potassium permanganate solution and osmium tetraoxide. The reaction is stereospecific and give cis-diol. Both OH group present on same site. Hydrolysis of epoxides. Glycols can also be prepared by acidic hydrolysis of epoxide. Hydrolysis of epoxide also stereospecific and leads to formation of trans-diols. Next is hydrolysis of dihaloalkane. Dihaloalkanes are hydrolyzed by aqueous solution of sodium carbonate. Reduction of dicarbonyl compound. Dicarbonyl compound are reduced by catalytic hydrogenation and give diol compound in which carbonyl group convert into alcohol. Reaction of diketone with Grignard reagent. This method can be used for preparation of higher vicinal glycols. Next is chemical reaction of dihydric compound. Reaction with metal. Glycols react with metal like sodium to form mono and disodium derivatives and liberate hydrogen. These reactions show acidic nature. In this reaction, ethylene glycol first react with one sodium metal and give monosodium glycolate, and which further react with second metal and give disodium glycolate. Rate of reaction of first step is very fast and second step is slow, so we need higher temperature. Reaction with hydrogen halide. Reacts with HCl and HBr to form two different products as shown. Reaction with phosphorus pentachloride and thionyl chloride. Glycol react with phosphorus pentachloride and thionyl chloride to form dichlorides. Reaction with nitric acid. When heated with concentrated nitric acid in the presence of concentrated sulfuric acid, glycols form dinitrates. Dehydration. Dehydration of glycols give different product under different condition. When heated to nearly 775 Kelvin, ethylene glycol form ethylene oxide. When heated with anhydrous zinc chloride under pressure in a sealed tube, ethylene glycol gets dehydrated to form acetaldehyde. When distilled with concentrated sulfuric acid, glycol form dioxanes. Next is oxidative cleavage of 1,2-glycols. When treated with periodic acid or lead tetraacetate, compound containing two OH groups attached only to adjacent carbon atom undergo oxidative cleavage. The reaction breaks carbon-carbon bond and yields carbonyl compounds. Utility of reaction. In this reaction, we can find out structure of a compound. Consider the oxidative cleavage of three isomeric butane diols. These are 1,2-butane-diol, 2,3-butane-diol and 1,3-butane-diol. Only 1,2 and 2,3-butane-diol react with periodic acid, but 1,3-butane-diol does not react with acid because it does not have any OH groups attached to adjacent carbon atoms. Determination of number of OH groups present on adjacent carbon. In polyhydric alcohols, number of moles of oxidizing agent used in reaction also indicate the number of OH groups present on adjacent carbon. To determine whether OH groups are present in vicinal position or not. The occurrence of reaction between polyhydric alcohol and HiO4 is established by formation of a white precipitate. Next is pinacol-pinacolone rearrangement. On treatment with sulfuric acid, pinacol undergo dehydration with molecular rearrangement to form methyl tertiary ketone, also known as pinacolone. Mechanism of this reaction. First step is protonation of pinacol. In the presence of acid, pinacol first protonated and after that lose a water molecule and formation of carbocation. Third step is rearrangement of carbocation. 1,2 shift to electron deficient carbon atom to form a stable ion, and last is formation of pinacol. Thank you.